Okay, kiddos, here we go with a little explanation about the work done on an object. So here we see our friend, and she is pulling this box, and there's a rope attached to the box, and so just because of the way she's standing, she's pulling at an angle. And it looks like she's going to pull the box through this amount of distance, so it would end up over here. And what we're going to do is calculate how much work she does on the object. And a little review goes like this. So work, we can calculate it by force times distance, but if you're trying to conceptualize, well, what is it? It's basically the amount of energy you expend in doing something. So we did talk about the example of I thought this was a different slide. Whoops. We did talk about the example of the table with the books. And the table can support the books forever. So if you're sitting there, if this is you, if you're sitting there holding a bunch of books, you're going to feel like you're really expending a lot of energy. And that's just, well, I mean, you kind of are, but in terms of physics, you're not really doing any work. Yes, you're supplying a force, just as the table is, but you're not moving, you're not supplying that force through some distance. If you were to lift the books up, you would definitely be doing work. The table cannot do that without some form of energy input. So again, think about work as the amount of energy expended. It will be measured in joules. So here's a simple example. We have some person, they are exerting some force, 100 newtons, on, it looks like a 50 kilogram box. 50 kilograms, that's about 110 pounds. And what they're going to do is they're going to push this box through a distance of 3 meters. And we are interested in how much work does the person do. So we've talked about friction, and if we knew how sticky the ground and box were, meaning how much friction there was between those two surfaces, or the coefficient of friction, we could calculate that, and so on and so forth. But all we know is that the person is exerting this force. We don't know how fast this is accelerating. We do know that they push it through a distance of 3 meters. So it's actually pretty easy. The force is 100 newtons, the distance is 3 meters. We multiply, a newton meter is a joule, and this is our answer for the work. Notice how the mass of the box didn't even matter. We didn't find its acceleration. We don't know how much time it took to move through that distance of 3 meters. We do know how much work was done in doing that. So it turns out that you can sort of, if you accelerate something fast and it doesn't take a lot of time, or you accelerate something slowly and it does take a lot of time, you can end up doing the same amount of work. So this quantity work and its relation to potential energy and kinetic energy ends up being very helpful for us. Sometimes calculations are greatly simplified, and we like that. So second example, not so simple, is what we saw in the initial slide, where the woman, our friend, was pulling on a rope and there was some angle here. So here she is pulling with the same force on the same box and moving it through a distance of 3 meters. It turns out that the actual useful work that she does is only contributed to by the component of force in this direction. So she's kind of pulling up and just wasting some of her own energy. The useful work that she does is this force times this distance. We're going to use SOHCAHTOA. So it looks like this. The hypotenuse is 100 newtons, and then this leg is going to be the component of force parallel to the direction of motion, if you use your SOHCAHTOA skills, you'll end up with this, which means you'll end up with this, which multiply force times distance. We get this, which means this. So less work was done because less force was exerted in the direction of motion on the box. Hope that helped.